All right, guys, welcome to the seventh talk in the LLVM Social Introduction to Common Compiler Tools series. The first six talks have been recorded and they're on our YouTube channel, so you can find it there. So we'll get started with this one. So while we get started, just remember that we follow the LLVM code of conduct. Please mute yourself unless you are talking. The talk will be recorded and posted on YouTube. You can ask your questions either in the chat or you can unmute and ask. I prefer unmuting and asking because while I'm giving the presentation, I can't actually see that. So if you want to like have some immediate doubt on any slide, just ask. Otherwise, we can also take questions at the end. So let's get started. So this is a talk on code coverage. So, code coverage is one of the most important metrics in software engineering, and I think this is one of the talks that really goes outside the bounds of just being a compiler tool and being a tool that software engineers use in general. So, obviously, code coverage is not a supremely complicated idea. I think you'll get the gist of that in the next 5 minutes. But if I only told you what different code coverage tools would do, that would be no fun. So this time in this talk, we're going to be a little brave. We're going to try and uh, go into the compiler source code a bit. We're going to see how coverage actually works, all down to what algorithms it uses, how it impacts the assembly, what instrumentation exactly is. We'll compare the different kinds of code coverage. And for once, even though this is an LLVM social talk, the initial part of the talk will be all related to GCC and GCC's code coverage tool. So with that in mind, let's get started. So what is code coverage? So code coverage is basically the percentage of code that is covered by test cases. So let's say that you've written a program with many if statements, for loops, with many branches, it has many functions. So your code, and you run your code. So what part of the code regularly runs sort of depends on what inputs your users give. But as a programmer, your job is to ensure that all parts of your code is thoroughly tested. So how do you make sure that your test cases actually check all of your source code? So that's where code coverage comes in. So what does it do? Code coverage, basically, it simply determines which parts in a body of code have been executed through a test suite and which have not. In general, a code coverage system, it collects information about the running program and then combines that with the source information to generate a report on the test suite's code coverage. So basically, you have the source code and you have the information about the running state of the program. Like a particular for loop was taken 500 times, or an if statement was executed 10 times, and part one of the statement was executed some X number of times or some Y number of times. So both of these data are combined together to give you a report. So what does that look like? Let's take a look. So before that, why is it important? So code coverage basically proves two things and only two things. One is that it proves that your test suite is complete, that complete in the sense that your tests visit all your statements and all your branches, and it proves that there isn't any dead code. So basically, if there is some condition in your code that is rarely taken, but it is still there, then that is code that is probably not needed and it can cause unpredictable behavior when you do take that branch. So this type of code should be reviewed. I'd like to emphasize that code coverage, having a code coverage of 100% doesn't necessarily mean that your test cases are perfect and that your code has no errors. Far from it, there can still be runtime errors and other sorts of errors. But yes, aiming for a higher code coverage in your test suite is generally a good goal to have. So, what are the code coverage tools for C and C++? Of course, this is a system-centered talk, so we have a lot of system-centered tools. So, in the C and C++ world, there are some commercial tools which are Bullseye Coverage, FrogLogic, Coco, Testwell CP++. There's gcov, which is a free and open source code coverage tool that comes with the GCC compiler. This is used by a lot of companies, and the first half of this talk will focus on gcov, while the second half of the talk focuses on llvm-cov. And finally, there are code coverage metrics. So code coverage tools that show the percentage or fraction of statements, functions, branches that are covered. So yeah, there are lots of types of coverage basically. So there is statement coverage, which is a metric that tells you whether the flow of control of your program has reached every statement or not. Don't worry, we'll see examples very soon. There is function coverage, which tells you whether each function was invoked or not. There is branch coverage, which aims to ensure that each of the possible branches from each decision point is executed at least once. And this ensures that all reachable code is executed. So stuff like if statements and loops. So branch coverage also in branch coverage and condition coverage also has something known as MCDC coverage, which is modified condition decision coverage, which is the number of independent events that can influence a particular path in code. So this is represented as a truth table, which we'll see soon. And finally, there's condition coverage, which shows that each condition within a decision statement has been exercised or not. So like if you have a ternary operator, how many times was the first choice taken, how many times was the second choice taken, and so on, right? So gcov is, again, we come to gcov, which is a C++ coverage tool. It's a source code coverage analysis tool. It exacts the count. It generates exact counts of the number of times each statement in a program is executed. It can tell you branch probabilities, branch counts, function summaries, count of all the blocks, branches that are taken unconditionally. And there's a add-on to it, which is llcov, which we'll come to in the end of the presentation. And there's also gcover, which is basically the same utility, but written in Python with some extra features. So gcov is invoked using two compiler flags. Not gcov as such, I mean, the coverage functionality is invoked using two compiler flags, which is fprofile args and ftest coverage. And we'll see very soon what they are. So finally, enough of theory, let's come to an example. So here's a very basic C program. It's written in C. It loops over integers 1 to 9 and tests the divisibility with the modulus operator. So can anyone tell me real quick something odd about this code? Anything that you see ordinary, out of the ordinary? Some part of the code that's never executed?
The second condition?
Yes. So the second condition is basically never taken because our loop goes only from 1 to 10, right? So we never check for mod 11. So the second if condition is never really executed. So now basically code coverage does a lot with the compiler. So earlier we've explored Godbolt. So let's just do some stuff real quick. So here's the same C program. Hash include stdio.h, you have main, and then you have the for loop, and then you have the statement. So let's add a compiler, which is GCC compiler, I guess. Yeah, 1 second. Let's just drag this to the side. We have a GCC compiler, and let's add another compiler because we have to check for one difference, right? So let's put that here. Yeah, that should do. So the first one will just execute it at O0, default optimization, so that the assembly is not changed. Well, the second one will add our coverage flags, which is fprofile args and ftest coverage, right? So we'll add these two flags. So and then let's finally take a diff. So a diff as in let's compare the output of both of these. So this is our first example, and this is our second example. So this is the example with coverage on the right, the one where the green stuff is highlighted, and the stuff on the left is without coverage. You can actually see there's a lot going on. The assembly has changed, right? There's some move instructions, there's some add instructions, there's another move instruction, and it's there several times in the code. And finally, there's this huge gcov main thing, and there's a lot going on. So basically, coverage does a lot of things under the hood. So we'll take a look at that. What are those things that it's doing actually, and how it's doing that. So before that, let's just see what the output actually looks like. So I have my test.c program. I execute it with the flags f profile args, f test coverage, test.c, and then I execute the program. Obviously, to get any coverage data, you have to execute the program. So yeah, this is a program that doesn't take user input, but yeah, it won't make a difference if you have a program that takes user input, or if this a.out is replaced by test cases that run on your executable instead. It's all the same. The coverage tool doesn't care. So then I see that as soon as I invoke these flags, apart from my default a.out file, two different files have been generated, a test.gcda file and a gcno file. So the GCDA is a data file and the GCNO file is the notes file. And finally, it tells me that 85.71% of the lines have been executed, 100% of the branches have been taken, 83% of the branches have been taken at least once, and it has generated a .c.gcov file. Now on the right side, I've just opened this file in a text editor in gedit. And you can see that there are some numbers here. It's telling me that the for loop over here, the 10 that is there before the colon, it tells me that this loop was taken 10 times. Branch 0 was taken 9 times. Branch 1 was taken once for in a fall through. And there is line number 13, which is printed. Modulus D is divisible by 11. That is never executed. So that is the line that's never executed, and it's marked by hashes over here. So this is what a gcov output looks like. It tells you in numbers how many times your code has taken a branch. It can give you percentages also, and it can give you ratios. The output can be configured in many different ways. So these two files that were generated, right? This GCDA and GCNO file. So what are they? So GCNO file is generated when the source file is compiled with GCC ftest coverage option. So we have two flags, which is fprofile args and ftest coverage. So ftest coverage generates the notes file. So it contains information to reconstruct the basic block graphs and assign the source line numbers to the blocks. So that's your notes file. And your GCDA file contains the object files built with fprofile args. That contains arc transition counts, value profile counts, and some summary information. So the GCDA file has all of the numbers, and the notes file has all of the data on the control flow of the program. So how does this really work? So we have a few questions at this point, right? So what changes when we add fprofile args, ftest coverage as a compiler option? Is the flow of the program altered in any way? And how does the coverage data get counted and written to the GCDA data files? So one way to check this is, what kind of symbols have been introduced into the code. So a very useful way to just see symbols is the nm command. So here I'm executing GCC with -e. -e gives me the pre-processed output. The pre-processed output means that all of the macros have been expanded, all of the include files have been included, and any other code inlining or unrolling that had to be done is done. Test.i is the pre-processed file. And then I'm basically invoking the assembler separately with the AS command. So basically, I'm just executing the program bit by bit instead of just using the GCC driver to, execute the program all at once and without any flags. So here you have a main symbol and a printf symbol. So now we're doing the same exercise. Again, this is the same test program that we saw earlier that this takes for division by 3 and 11. But this time we've added fprofile args and ftest coverage. So now we see that there are a whole lot more symbols. There's a gcov init symbol, there's a gcov exit symbol, there's a gcov main symbol, there's a merge add symbol, there's a global offset table. So we can compare and analyze the assembly code before and after the coverage and then discuss the analysis of the instrumented code. So from Godbolt only, this is the program that corresponds to the assembly on the right. So here again, you have the same C program, and here you can see the assembly. It's fine if you don't understand assembly. What we have to focus on is what changes, right? So assembly after coverage. So all of these black boxes that you see on screen, all of this is stuff that has been added by the coverage tool. So every time there is a move instruction and the racks counter is incremented by 1. So this racks counter, racks instruction is incremented by 1. For each part of your program, the same racks instruction is incremented by 1. And finally, there's this really long data structure that has that is labeled .lpbxo, and that has a lot of separate counters. That's in gcov main, right? So there are totally 7 stub codes that have been inserted, out of those which first 6 are very easy to understand. It's a counter, and as long as the relevant code is executed every time, this counter increases by 1. So we can see from the stub that the function to be completed by this code is to increase this counter by 1. But what is the counter? So the counter, racks counter, is a long integer of 8 bytes composed of this .lpbxo and gcov main. So the first 6 stubs are actually for a static array with 6 long integer elements. The size of each counter is 8 bytes. So this is a read-only data structure, and basically here in this gcov main thing, all of the counters are incremented. So the last stub that is inserted, the .lpbxo, it's always the same regardless of the contents of program. Whether your program has any branches or not, that is always there. So it's like a constructor. So this is a function called gcov main, and the calling parameter is the lpbxo structure. So using the object dump command on the executable file, we can see the symbols, right? So there is a way to visualize this, to see it visually. So GCC has an option to dump all the output of all the passes. So you can do GCC fdump tree all, and like since the data is still not very easy to parse, you can pass it through a tool like the dot tool, which can convert your optimized dot files into a PNG that you can visually see. So you can see that this is your main program, and your main program has different basic blocks. A basic block is like one unit of execution, and you can see that 2 additional functions have been added: this gcov init and gcov exit. Gcov init to initialize and gcov exit to exit. So finally, when you go to the GCC compiler source code, you can see that it's defined in libgcov driver.c. So from here, you can basically draw 2 conclusions. So this data structure is gcov info, and these two are the same thing. And the gcov init features this data structure strung together as a list, and the list pointer is gcov underscore list. And finally, like inside GCC source code, there's a file called gcov.c that describes how these cycles are actually counted for profiling purposes. So fun fact, GCC used to use a different algorithm to actually do the counting and to count the cycles. So a cycle in the code. So basically now they use an algorithm known as Havik cycle detection algorithm. It's used to find the simplest paths in the subgraph. There's a paper on this algorithm. You can read it. It's quite interesting. The function for creating solution for flow graphs are basically taken from profile.c, which is used for profiling. And all the other file formats of GCDO and GCNO are documented in gcov io.h. So basically, that was a compiler deep dive into the gcov compiler tool. So let's go back. Yeah. So now we've understood, like inside out how gcov works, at least in the GCC compiler. So, and yeah, what it does. So it can give you coverage counts. It can give you counts for lines, statements, functions, branches, right? So there is a similar tool by LLVM. It's called llvm-cov. So this I can actually show you. Let's see if we can see it here. Let me just zoom this in a bit. So let's take the ls. Okay, let's remove all our extra files. A.out, default.proc data, default.proc. So now we have a test.c file. Is a test.c file. It's the same file that we saw. Right? So first step is uh, we have to compile the file with the flags that we have for Clang. So the corresponding flags for Clang are actually f profile inst generate and f coverage mapping. So let's see if my Clang is detected or not. Okay, I don't have a Clang. Never mind. I'll have to go set that. So let's go do that. llvm-cov. Yeah. Yeah. So with Clang, do I have a Clang now? Yes, I have a Clang. So Clang F profile instrument generate, and then F coverage mapping, G for debug info, W all, and finally test.c. So okay, that executed just fine. Now we have to actually run the program, right, to generate the coverage data. So you have 3 is divisible by 3, 6 is divisible by 3, and 9 is divisible by 3. So then the way that LLVM code coverage program works is actually a little bit different from GCC's code coverage tool. It does not rely on generating GCDA files or GCNO files or any of that stuff. It directly uses the AST. So let's see. So you have to, there is a prof raw file that will be created here. And we're basically going to create a prof data file. So using LLVM prof data merge. So now we can finally do LLVM cov show. Like after we've generated this file, we can ask LLVM to show us the output. So instrument profile, minus profile, default. Yeah. So data, stuff. Let's hope this works. Okay, it was nice. So we have our stdio.h. So this is the line count starting from line number 1 to 15. And here you have the count of how many times each statement is executed. You can see the for loop is 10 times. And we've entered this statement 9 times, the first if condition 9 times. We've done the printf 3 times, whereas this second printf is executed exactly 0 times. And finally, we return once and then exit the program. So there are few advantages to the way gcov's llvm-cov's coverage tool works compared to gcov. So it works by counter to source region mapping. So basically, while the abstract syntax tree is generated, it at that time only the mapping is done, and then the counter instrumentation is done in llvm-ir. But since the AST is directly lowered to llvm-ir, this gives you an advantage. The advantage is that since the AST is immutable, in gcov we have a problem that if you execute your program at say a very high optimization level, something like O3 and with FLT or something, so then your compiler might do optimizations. So we've discussed a few optimizations. Your compiler might eliminate dead code. It might unroll the loop. It might inline some function. It might do strength reduction. It might replace some code with some other equivalent code. It might reorder the code. So basically, your final executable does not correspond one-to-one to your like original source code. You have there's some noise in the background. Is anyone unmuted? Yeah. Some yeah, I think now it's gone. So yeah, so basically the problem is with gcov is that if you have very optimized, like if you're running at a very high optimization level, your compiler is doing certain optimizations that reorder your source code. I mean, when it's so your assembly or your final executable, it no longer corresponds one-to-one to the source code. So basically, the counters will not work. Several of the counters will be wrong. Several of the lines will show as never executed. However, in LLVM curve, because it's done at the AST level and all of the optimizations come in LLVM after the AST is already generated, llvm curve doesn't have this problem. So it works with even then. So finally, then there's your test execution phase. So after your profile done your counter instrumentation, you can execute the test and then you can visualize the data. So Alan Phipps has a very nice talk on this in the LLVM dev meeting. You can go through that. So the output of both of these compared, what do they look like? So GCC's HTML looks basically like this. If you use llcov, we'll come to what is llcov really. LLVM's HTML looks a bit different using llvm-cov show. And the text view is also very different. The LLVM stuff is a little more nicely formatted. So this below here, it's an example of MCDC coverage, which is modified condition decision coverage. So we have bool true for int x and y, and then we have an if condition where uh, with the logical and this thing operator. So here you have a truth table basically. When are both of these statements true? What happens when one of them is evaluated first because compilers do short circuit evaluation? What if the first one is false? So you can see the truth table and it will give you the coverage for each of those in the truth table. So this is the MCDC coverage. So what are the features of llvm-cov? So it's got some really nice documentation on the LLVM website, even though it might be a bit hard to parse. So you can go check it out. Here's the documentation on the LLVM docs page. So there's a lot of features that it allows you to do. It allows you to use regular expressions to filter out your report. It allows you to filter your report based on function names, regular expressions, directories, files. You can output the report in plain text in HTML, in llcov or JSON. So JSON is useful if you want to do some additional processing on top of the coverage file before converting it to a report. So basically, there are two tools here. One is llvm-cov gcov, and one is the llvm-cov. So initially, when the Clang and LLVM project was young, they built a version of gcov themselves that's actually compatible with the GCC version. So you can use llvm-cov gcov and generate a coverage report that is exactly like GCC's coverage report. Although it's a bit outdated now because it's only compatible with gcov version 4.2. And you can also export summary information at the file, function, region, or directory level. So here are some coverage reports using different visualization tools. So gcover and llcov are not coverage tools. They are tools that help you visualize the report in a more efficient manner that is generated by gcov or llvm curve. So gcover is the newer project. It's designed to be like Python's coverage utilities. It uses gcov data. It supports XML and Jenkins integration. So if you want to use code coverage with Jenkins, this is very useful. And it's written in Python. llcov is the older project. It provides a graphical front end for gcov. It's a part of the Linux test project. Basically, it's used for coverage in the kernel a lot. It's written in Perl, so that is a bit hard to modify and work with, but a lot of places still do use llcov. Then there's also the llvm-cov show HTML, which is the graphical front end of llvm-cov. Recently, it has gained support for a nested directory view. It's fairly bare bones, but there's some real nice stuff. Like, let's say you want to see the coverage of the entire LLVM compiler itself. So you can go to lab.llvm.org and click on coverage. And then you can have the coverage of the various projects. Like here you have LLVM, you have include, and you have LLVM, and you have all of these files. So you can see here, I'm inside CodeGen, and I can see the coverage of each and every file. If I want to get even more specific and go inside each file, I can even do that and just go inside each file and see the coverage. So these are header files. So I guess here it's no good, but let's go to Clang. So let- let's see here, ST matches. Yeah, here we have a CPP. That's nice. So we have a gtest matches.cpp, and here it's telling you the coverage counts for all of these, including which lines have zero coverage. So basically, this default case, LLVM unreachable, unhandled microtype enum. There's no test case in the LLVM test suite that hits this condition. So basically, this coverage report is generated against the LLVM nightly and LLVM test suite, and then they test, like, how much of it is actually executing. So then you also have tools like codecov. So if you're an avid open source contributor, you might have come across a lot of projects using codecov. So it's a product by Sentry that integrates code coverage tracking into various hosts such as GitHub, GitLab, Bitbucket, and it works with a lot of languages. You can also upload reports to codecov for historical tracking. I believe codecov recently went open source, so that's great. It's not a code coverage framework by itself. That just to clear that, you still have to use your language's code coverage tooling and configure codecov to pick up your reports. It's just a really nice overlay that can, like here you have codecov commenting on a GitHub pull request, that what is the coverage of this particular pull request, and after this pull request went in, did the coverage go up or did it go down? So if you care about coverage, then the only way to really enforce it is to do coverage at a per patch level. So like, let's say you have a compiler or you have a C++ software. So you want that every time your developer submits a patch, they submit it with the appropriate test cases, and such that at least their patches code coverage is as high as possible. So in practice, that's how it's implemented. So till now we saw code coverage of really small files. So let's take a 100,000 feet view, code coverage for really large applications. So here is the code coverage report that I generated last year for the entire LLVM source tree at the time. So this has about 17,89,309 lines, and out of which about 14,31,000 have been hit. So the LLVM test suite hit about 80% of the lines, which is actually a great number if you ask me, considering how big LLVM is and these many functions. So here I'm not specifically talking about code coverage for compilers. I'm just using compilers as an example of a large C++ program that you can compile. So how do you build something as big as a compiler with code coverage? So when gcov is used for coverage, ideally you have a target application, a compiler, and you have to set up I am back. So sorry for that. Let's share again. Yes. So where did I drop? Can somebody please tell me at this slide or before this slide? Hello?
This slide itself, yeah.
Yeah, this slide itself. Right? Okay, cool.
Yeah.
Not too much loss then fine. So when gcov is used for coverage, ideally you have to select a target application, a compiler, like because you need a compiler to do coverage. So here I'm considering the fact that you have a C++ application and you have a compiler to compile it with. So your compiler is going to have a build system. So it's either going to use, I mean, your application is going to have a build system. In this case, the application is also a compiler. So you can have either CMake or make or whatever else you use. So over there, there's going to be a place to pass CXX flags, and you can use gcov to then generate the coverage report. So for example, if you want to build Clang with coverage, we use the Clang build process in which Clang is the application. So then at the end of the build process, compiler build process, you have make check all, which basically covers all the tests executed. The coverage report can be added by adding the CXX flags and linking with the libgcov library or by using CMake modules. So CMake modules are just basically pre-written pieces of script that you can invoke in your CMake. So here are some examples that can work. So let's just take a look at one of them real quick. So basically, you're not doing anything too fancy here. You're just adding the coverage flags. So let's take a look at this one and the other one. Yeah, here. So this is basically a module that's used for enabling coverage. So let me zoom it in a little bit. So you're checking if your compiler has support for coverage or not. If it matches the string, then you have to add coverage flags. So it's adding the flag dash dash coverage and my hyphen G. So dash dash coverage basically is a shorthand for F profile args F test coverage. And then you add F profile absolute path because you want to take care of paths and all that. And finally, you build the compiler without any optimizations. So you set coverage compiler flags and you set it to hyphen G and dash dash coverage. And finally, you can basically you make the modification in CMake. So in your llvm project slash llvm slash CMake list.txt, you can just add a module that set a CMake module path. This is my module path. And then if the compiler is GCC, then include code coverage, add code coverage end. And in my CMake command that I use to build the compiler, I just use the code coverage is equal to on, and that builds my compiler with coverage. Finally, if you want that report that I showed you in the beginning, you can use llcov. So for that, you do you of the llcov project, you collect the coverage data and you have to write it to GCDA. So using this command, you can do that. So it has two files, geninfo and genhtml. Geninfo basically takes all of your different GCDA files and glues them into one info file that has the coverage of the entire project because you have multiple C++ files. And then Gen HTML finally uses that info file and generates one giant coverage report with directories and everything. It's like how you saw for llvm-cov or for the llvm project time. So llvm also comes with the built-in sanitizer coverage. So this is sort of bare bones. Basically, if you want to do instrumentation-based coverage instead of the AST-based coverage that llvm offers, you can do sanitizer coverage. So it inserts calls to user-defined functions on a block, basic block, and edge level. Sanitizer coverage doesn't go all the way to statements. If you want statement level coverage, it's probably better to just use llvm-cov instead of using san-cov. So you can cover edges, basic blocks, and functions. So when you turn on fsanitize coverage is equal to trace PC guard, this following code is inserted on every edge. So this mechanism is used for fuzzing the Linux kernel, and there's more information on it on LLVM's website. So basically, that brings most of the talk to a close. Yeah, I think you all already know where coverage is used and why it's important. So we covered some basics on how it works, how you can use it in your own C++ project. So the references, you have gcov documentation and llvm-cov documentation. There's a nice talk from LLVM, their meeting that you can go through. There's also LLVM projects coverage report that you can see that I showed you. There's codecov, the sanitizer coverage, and I gave a talk on code coverage for glibc earlier. You can go through that also if you want. We have some important links to stay updated with the LLVM project. You have the LLVM Weekly, you have the LLVM Discord server. So LLVM Weekly is a newsletter by Alex Bradbury that outlines, all the important things that happen in LLVM project and all its sub projects over the last week or so. It's a great way of keeping updated. There's the Discord server where you can ask doubts and chat with people. There's the discourse page, which is a more formal forum for stuff like RFCs and long-term decisions. And if you want to have a long chat about why something is implemented the way it is in LLVM, it even has a beginner section. LLVM also has a YouTube page. They've also started an initiative known as Office Hours. So if you want to talk to some senior LLVM developers and get their input on something, you can block their calendar. There are project-specific meetings, so if you want to get involved in LLVM or in a new project, you can do that. And finally, there's our meetup page and our YouTube channel that you can follow. Pradeep or Prerna will put the link to the YouTube channel and a WhatsApp chat that you can join to follow the other talks in this series and the offline meetups that we have. So that brings my talk to a close. I think I've been speaking for about 45 minutes, and I'd be happy to take any questions.
So these
I think there was some echo. Please, can you repeat? Hello?
Yeah, sorry,
Yeah.
we of us are in the same room, so it got an. Uh, my question was, you need to have extensive test suites to work on this, right? Otherwise, it wouldn't be so useful. The projects have to have extensive test suites to run.
So yeah, that is one point that the project should have tests to run, but there are some points that I'd like to say where it's still useful, even if you don't have very large test suites. One is that it might be useful in enhancing whatever little tests you've already written. And the other thing is that you can use it to sort of figure out what the most frequently executed parts of your code are. Like, I don't know, let's say you have a chess engine, right? And you build it with coverage and then execute it and then play a few hundred games of chess. Then the coverage report that you get, it's not from a test suite, but still you will know what your most hit code is. So it's a very rudimentary kind of profiling in a way. You can get to know what parts of your code got executed the most. But yes, code coverage is not supremely useful if you don't have a test suite. The entire point is that you have some kind of test suite or you're in the process of developing some kind of test suite and you want to know how good it is for your application. Sometimes we also use it to test potential test suites. Personal example in compilers would be that there are several test suites for the GCC compiler and for the G-Fortran compiler. So our team in AMD, we work on a Clang-based compiler that's based on LLVM. So the GCC's test suite might still be useful for checking the coverage of LLVM, provided it executes the right parts of code. But the only way you can know that is by generating different coverage reports. And there's something known as a differential coverage report also, where you can basically build the application with coverage and then test it out with workload A and then test it out with workload B and then take a diff of that to know that, what parts of code did the application execute against that was unique to A or B. So that way you can like sort of build up a subset of applications or test suites that cover your whole thing entirely. Like in isolation, one of those might not cover your entire thing, compiler or workload or application, but together all those workloads will give you a very high coverage. So I hope that answered your question.
Yeah. One more question. So you used llvm-cov itself to generate the test report for LLVM?
I use the gcov in this example just to contrast it because like if I use llvm-cov, then yes, llvm-cov is specifically built for like llvm-cov has some special features for covering LLVM. But in this case, I just wanted to show how you would cover any application. So that's why I use GCC's coverage tool to cover LLVM in the example that I showed you. Yeah.
Okay. Yeah. Got it. Thank you.
Any other question?
There is one question in the chat. Manoj Kumar.
Could you also explain what do you mean by MCDC coverage? Okay, so MCDC coverage. So yeah, it stands for basically modified condition decision coverage. So it's sort of like, how do I explain this? You have some conditions like it's a criteria. It's basically a criteria that's used in software testing. You're saying that you have to show the independence of a condition that by showing that only one condition changes at a time. So if you have like say a Boolean condition, you have to prove that only, how many of these changes are independent. If I take one path, if I take one condition, is it independent of the other outcomes or not? So independence of a condition is shown by proving that only one such condition changes at a time. So it's basically a modification of your condition coverage or decision coverage. And the reason I mentioned that was the project I worked on was for ISO 26262, which is basically an automotive standard. So over there, it's sort of important because cars are required to, any software that goes into cars or automotive has to have complete MCDC coverage. So yeah. Anything else?
Hello.
Yeah.
Yeah, I have one question.
Yeah.
I'm just asking, how will the tool profile the code if the inputs to the program are taken from the any input device or from the external world, and how we will test or develop a test suite for that, or basically profile that code?
Okay, so yeah, that's a good question. So first of all, profiling and coverage are slightly different things, but in the case of gcov, for example, the moment you generate your executable and start executing that executable, when your executable is generated, the executable itself has the instrumentation that is done for the coverage. So the GCNO and GCDA file, right? So your notes file is your GCNO file is constant because that just has information about the control flow of your program. The control flow of your program is not going to change through its execution. The only thing that will change is the count, right? So as you keep executing the test, like, you keep working through the executable. As you execute the executable and you're feeding it any data, like through the terminal or through an external application or even through a test suite, the GCDA file is continuously updated. And when you're finally done, and when you invoke a command that, okay, I'm done, and now I'm generating the report, then that coverage information is used. So all of the instrumentation is done at compile time, and at runtime you're only updating the counters. Does that make sense?
Okay. Yeah.
Yeah.
You showed one report which you generated an year back for the LLVM.
Yeah.
What did you compile with the instrumented LLVM binary?
Yes. So I think I mentioned it, but I checked the output of check all, make check all. So LLVM has its own test suite, right? LLVM lit. So that is what executes at the end of compilation. Like if you basically build the compiler and run make check all or ninja check all, then it runs a series. It runs check LLVM, check client, check compiler RT. So there are around 80,000 or so unit tests in LLVM itself. So that the output was related to LLVM lit. That was my test workload.
Okay, thanks.
Yeah, sure. I also think, just to add on, I also think the report that's hosted on lab.llvm.org, that is also against checkall. I think they use the LLVM nightly also, but I'm not sure. I haven't compared the reports. Okay, any other questions? What coverage parameter does the tool under consideration focus on the most statement, line, condition, or branch? So the tool doesn't have any focus. It depends on you. Like statement coverage might not be very important to you if you have enough function coverage, or maybe sometimes condition coverage is very important because some conditions are never taken. So you have switches in gcov, like you have, or in llvm-cov, you have hyphen branch, hyphen condition, or by default it is a statement. So you can choose what kind of report you want. You can get coverage of all of those things at once, or you can get coverage of only some of those things. Or if you want, you can even not get file level coverage. You can get only summaries, like coverage of the entire directory or something. It all depends on what level of granularity you want in your report. So depending on what metrics are important to you, you can choose the right set of flags while generating the report. By default, the tool is going to profile everything. You can choose what of it you want to export to the report. Also, can we get an idea of the number of test cases by looking at parameters like cyclomatic complexity? So I'm not sure I quite got what you mean, but yeah, I mean, if you mean how can we know the minimum number of test cases needed to get a good number of coverage, that really sort of depends on where you're starting off and like how big your application is. Or you don't necessarily need 100% coverage all the time. It's not necessary or sufficient or even a good thing to chase after, because in compilers, you might have test cases or you might have conditions that can only be reached when you hit a segmentation fault or a memory leak or something goes horribly wrong. So sometimes simulating those conditions by means of a test case is really, really difficult. So getting 100% coverage is uh, probably not always possible. I think somebody has their hands up. Uh, Manoj, do you have any?
Yeah, am I audible?
Yeah.
Yeah, I had a doubt. You said the main difference between gcov and llvm-cov was that llvm-cov generates its artifacts or the counters at the AST stage, right?
Yes.
So after the AST stage, a lot of passes do happen on the compiler and a lot of name mangling, etc. does take place. So how does it still keep track of which particular code line it tracks? Does it use the location info embedding or any other thing?
Uh, as far as I know, it uses the location info from the AST because the AST itself is immutable. even if the LLVM IR after that can change. But honestly, I'm not 100% sure. I'll probably check back and get back to you. I'm not too sure about the internals 100% because I've used gcov more than I have llvm-cov. But yeah, I'll get back to you on that.
Yeah, I probably think it uses the location for two because it's harder to track from any other metric.
Yeah.
Yeah. So there are, sorry to interrupt, but there are nuances like when you instrument at AST level, the thing is the counters will correspond to the source line of code, right? So it doesn't matter like what optimization you do. If those counters are still alive, I mean, it is possible that some counters can get deleted with some optimization. It's rare, but it is possible. Now the thing is, so many optimization will run later on. So what happens is, because those extra instructions are there, the code coverage instructions, some of the optimization may not happen as effectively without coverage. So there are a little bit of nuances, but for the most part, like you can say like 80-90% of the time, you are still better off with having code coverage than without. On the other hand, when we have this instrumentation later in the optimization pipeline, let's say gcov or LLVM would also have later on, what happens is that time you are also exercising the compiler optimizations. So let's say there is a miscompile or something, some weird things happen in the compiler. So that also you'll get some insight into like why some counters are updating, why some are not updating. But like later instrumentation is mostly for like technical people, like compiler people, like that, and they get a lot of benefit from there also.